Let's jump to hypothesis testing. So we're going to change the chapter. You still have some chapter 7 problems to work through. So keep working through those. I think a lot of what we built up to is chapter 7 and talking about estimation procedures. We did some computation along the way. We compared different inferential approaches. Sometimes you get the same answer, sometimes you don't. And probably my take-home message about all of it is likelihoods are really important. So they're kind of the guardrails on a lot of inferential procedures. Puts the parameters in the right ranges. You know, on its own, the MLE might not be the best answer, but it might be a step into the right answer. So, like the uniform example where everything is budged against theta, the maximum or the minimum, depending on which side theta is on, is the MLE. You know, but typically you might budge that MLE over and move around the MLE. So it does turn out that that bias correction that I ended up presenting to you in the original code, where I just took one of those little 1/n increments and I multiplied the maximum by that increment just to kind of shove it over, is the unbeatable unbiased estimator. So it's minimal variance. You would need to know about completeness to prove that. So that is that Neyman-Pearsonians stuff. So Kramer-Rao doesn't work there, but you could still say, I've got this estimator, I can derive this under different lenses, and maybe later on in an advanced inference class, you can prove that nobody can beat you with it. But from an engineering or a science standpoint, if you used it, you would know it's pretty good. So anyway, that is what I would like to consider the point of my class. I will give you some warning shots about hypothesis testing, but I want to give you just the basic structure without a lot of philosophy here. So we've got 2 weeks to do this. Hypothesis testing. Yeah, let's just start easy. Write down the goal. The book says something about this, and I have a slight rephrasing to it. So the goal is to, based on a sample, so I might be thinking something like this. Xi's are coming from some model f of x given theta. I goes from 1 to n. Maybe everything's IID and everything is simple, but you basically have some sampling model that gives you a bunch of data. And you want to decide between 2 or more hypotheses which one is, and this is what the book says, true. This is the book. I'm just going to add a caveat. I've never really accepted any of this stuff. I get philosophy, I get the Popperian view. You can never know anything is true. You can only falsify things. That is true philosophically. But at the end of the day, we make a decision and we do something. So I'm not going to go into all the language about, no, you can't accept, you have to fail to reject. You know, all of that. At the end of the day, if you make a decision, you've accepted it. So, you know, when AI takes over the world, we're going to accept their decisions too. So be careful with all of that. So we're not going to be able to say, hey, wait, that's not true. But it's doing something anyway. See?
So are you getting at, like, in the sharp test, if you're saying is theta equal to something or not?
I'm saying it for all comparisons of all hypotheses.
Okay.
It could apply to the sharp test, it could apply to any test. So they just like this word true. I don't like the word true. I don't believe in necessary truths. That's true. I tend to think a lot of things can be true simultaneously. I don't really know what's true. The only truth I've ever known is that I'll never know the truth. So that's the only thing I can ever be certain about. If I did know the truth, I just got lucky. So I can be close to the truth though and say it's an operational truth. So I just think about this a little bit differently. Anyway, I'm going to shut down the philosophy lesson. So I'm just saying, is most compelling. And this is really what everybody's doing, is they're just coming up with compelling hypotheses compared to each other. And so we have to come up with different techniques that can wean out the more compelling things, and the different branches of inference have different ways of doing that. And there are sometimes, depending on which hypotheses we're comparing to each other, sometimes there's agreement between the techniques, and sometimes there's just utter gross disagreement. And the different paradigms will not agree. We'll talk about that a little bit later, but I'm gonna mostly stick to the book. So I've never been super successful of trying to go through all the nuance in 2 weeks on this. I think it takes a year or two for people to study, do model selection problems, which is a type of hypothesis testing really. That's where we'll end the base class, is I'll say, here's how you implement all this stuff. So all this stuff I don't like talking about, here's what you do with it. So, so this is my version. Okay. So different hypotheses might be things like this. So I might have some model set up like this that contains some parameter, and I want to ask questions about the parameter. David?
No, it's also a bit about what are the stakes in setting your hypothesis. Like if you're cooking chicken and your hypothesis is it cooked? Well, the stakes for accepting that it's cooked, you're risking salmonella. Well, if you accept that it's not, you're just risking having to wait a little longer to eat.
Yeah, I agree. That would be the right way to really formalize all of this, is put a real loss function on your decisions. And so there will be a correspondence between everything I've said with loss functions, risk, and power functions that we're going to get into. There is a connection, they do talk about it in the book. So it's towards the end of chapter 8, and I'm not going to go through it. So, but yeah, there's an absolute connection between all of those two things. I think to formalize all of this and get us all to agree, we would need to accept that we're all operating under the same loss functions. And then we can agree. There's subjective choices. Setting things up and saying that we're really talking about losses and risks and optimizing those and getting us to think about what the loss function means is probably a step towards us agreeing. So I will say this, Jim Berger, which is probably one of your more famous Bayesians, he used to not be a Bayesian. And it was exactly that sort of rationale, decision theory, and defining what the actual loss functions that convinced him that averaging over stuff and being a Bayesian might be a good idea. So he kind of switched his paradigms. So it was all through that decision theoretic thing. So I don't want to gloss over that like it's not important. I do think that's super important. We just won't get fully there. So, but I'll try to explain that a little bit differently as well as some examples. Okay, so let me just tell you about different types of hypotheses. This is all Stat 101-esque stuff. So for instance, we might, I'll say examples, we might test something like this. H naught is mu, or I'll say theta. Theta is greater or equal to theta naught versus H1, theta is less than theta naught, something like that. So you might do something like that. This is called the null hypothesis. And this is what you're testing against, usually called the alternative hypothesis. Sometimes people put an alpha there and call that the null hypothesis. You've all seen this stuff. So there is a license plate on campus that says H0BSH1. And so already, that's not my view of the world. So I don't think I can get along with that person. So I just avoid it. So anyway, I don't think this is the end all be all of statistics. I think this is mostly the black eye. This test is not, this is somewhere where a Bayesian might agree with each other. So we'll talk about why that might be maybe on the last day of discussing this. So this isn't a very contentious sort of test. I want to just say Then if theta was continuous, the cardinality of these two sets is the same, so making a comparison between these two groups is probably reasonable. So if you did compute like if this was mu in a normal distribution and you were computing a p-value for this, the p-value under the flat prior would be the Bayesian posterior probability. So there is correspondence to those two things. If I ended up reversing the hypotheses, the one minus the p-value for this problem would be the p-value for the reverse problem. So there's kind of a complementary action there, so everything is very adjustable to other hypotheses. And so I would say comparing this set to that set does make sense, and mathematically all the different paradigms seem to agree on tests like this, or at least pretty close. This is called one-sided test. So there's also stuff like this. H naught, I'll say theta is equal to theta naught, so that's just a point. Versus H1, theta is equal to some other point. Theta 1, some other point. Mostly, for the most part, Bayesians and non-Bayesians, Neyman-Pearsonians, and probably Fisher would all agree on this. They might not agree on the interpretation exactly, but they would probably give you very similar measures of belief between these two different hypotheses. I phrase that like a Bayesian, so if you want to phrase it some other way, you can. So, but this isn't super contentious either. This is the contentious test. So H naught versus H1, theta is equal to theta naught, that's the point. And then I might say theta is not equal to theta naught. And I might be thinking about this in a continuum. So this is a whole set. So possibly if theta was representing mu in a normal distribution, this would be saying I think mu is either a point or I think it's any other number on the real number line. Just the way I said that already sets this up to be ridiculous. So I find just at glance a problem like this. If I think data came out of this and I'm looking at a continuum, I glance at that and I go, I'll take the alternative, thank you very much. So you remove one little point from it and say anything else can be true, there's no way you pick the right theta value. So it's an absolute question, this is ridiculous. So we can't actually mean this. So, but the Neyman-Pearsonians and the Bayesians feel very differently about this. So I'll say this is the problem where there's gross disagreement that starts most of the fights. But on the surface, it's kind of a silly question. I do get it. If you were doing a regression model and you were trying to figure out which covariates were important, which x's are important, beta coefficients in front of those x's that were really small compared to other beta coefficients on other x's, assuming that everything had the same variance level and they were scaled the same. A low beta would correspond to an x that wasn't providing much information about the variability of the y's. So at some point, you want to be able to say, is it a 0? Could I take it to be a 0 or not a 0? And I understand that is a form of this problem. So it is compelling to do that. So it's really the question is how close do I have to be to theta naught before I'm willing to, or I should say, how far from theta naught do I need to be before I'm willing to reject it? And that's what everybody is disagreeing on, is that notion of closeness, how they're comparing distances, how they're thinking about distances. So Bayesian is going to be very relative. And they're going to be comparing things in a relative sense, this compared to some measure on that. And they're going to be making a direct comparison. If you've ever computed a p-value, if we replace this distribution with normal and theta was mu, you've computed answers like that, and basically we're going to ask questions like how far is x bar from whatever your hypothesis value is. And they're treating things in a very different distance sense. So the p-value that's computed doesn't use the alternative for anything. So the alternative, when you're computing a p-value, just tells you the tail direction you're supposed to march down. So you would use this information right here to think about the tail direction of how you accumulate that mass in the p-value. Very typically, you'll see people write the problem like this. So this is maybe how they would introduce this to you in a Stat 101 type class. And it's because on the boundary of this thing is where you get the most power to detect, if it's theta naught or not. So that's actually what you would plug in. If you think about what a p-value is given the null hypothesis, what's the probability of observing your data in more extreme data where extremity is defined through the alternative. The test really is testing that whole thing. But you have the most power to detect here, and in terms of the phrasing, if I'm going to condition on the null hypothesis, conditioning on a set doesn't make sense. I need to plug something into that set. And so we'll talk a little bit more about that, but the test really is comparing this to that, the complement of it. So we'll talk about that a little bit later. Those are the different types of tests. This one is called the sharp test. Or I'll say the simple versus complex test, where this is a simple hypothesis and that's a complex hypothesis. Or you can consider this composite. So there's a lot of different synonyms for the exact same thing.
Was sharp a guy or sharp?
It's sharp because it's a point.
Okay.
So it's like the sharpest function I can think of. So it's infinitely thin thing that looks like something sharp. And so it's sharp compared to this thing that is alternately used. So that is a contentious test. It's no surprise why, because it really is, what do you even mean by that? If I were placing bets and theta could have been anything, I know what I would bet on. So we can't possibly mean that absolutely. Okay, this one right here is called the simple versus simple test. This isn't very contentious either, and in fact, a Bayesian and a non-Bayesian would agree almost entirely on this. They might not agree on the thresholds, but that's a subjective choice. The way they would set up the test would look extremely similar. So the Bayes factor and the likelihood ratio test statistic will be exactly the same. So if you've taken a Bayes class already, you know that that's true. Anyway, that makes sense. This is a perfectly reasonable comparison. So it's usually when you muddy the question, that's when everybody starts disagreeing. When you give all these possible interpretations to what you could possibly mean, you don't close the loop and tell us. So for hundreds of years, nobody's ended up closing the loop on what are we talking about when we're even talking about this sort of stuff. So lots of disagreement on that side of the board. Lots of agreements on this side of the board. Nobody will ever agree on this. So when I see this, I wince. I've been accused by an editor, one paper I wrote a long time ago, and the editor said, it seems like your statistician refuses to do a hypothesis test here. It's going out of his way to not hypothesis test and just compute a p-value or something like that. And basically, I said it's an estimation problem. So I like to turn everything into estimation problems if I can, talk about them that way. I do hypothesis testing periodically. I have computed a p-value before and published it. It was a one-sided thing, and I thought it really doesn't matter how you conceptualize this. I'll just do it what's comfortable for the community. So anyway, I don't like doing this kind of stuff. In my Bayes class, I'll show you how to set up MCMCs to do model selection, and basically I'm just going to explain what the trade-offs are in all your decision making, and then I'm going to give you some simulation studies so you can play around and observe those trade-offs. I think there's no absolutely great answer to questions like this, but I think that there's lots of things you should be thinking about. So I think that this could be phrased as a correct question if you ended up saying something about what a meaningful distance was on this. So the Neyman-Pearsonian takes that distance in some probabilistic absolute sense, which I'm not sure is exactly what we should be doing. I will point out Neyman-Pearson never actually advocated doing what's called the Neyman-Pearson paradigm. They were trying to explain to Fisher what he might be thinking about, and they never actually did it themselves. That whole framework has taken over the whole scientific world. So I would say that sort of problem is the problem we see all through science and engineering, and it's probably the grossest problem to even touch. So we do see it everywhere, so people need to be aware that this could be problematic. So I will say, if you're doing the whole p-value thing, all you have to do in a setup like that is just go collect more data. And you'll drive your p-value down. You can actually do that with almost anything, but you'll do it here really fast. The basic presumption is xi's came from some f. So I've got this basic setup, that framework in mind, and in a lot of cases it doesn't, we can be approximate about our f's, and we still get good estimations on thetas. What we could be doing when we're doing something like this, if we plug that theta naught into here and we see how compelling the data looks compared to that, what you might be rejecting is not your theta, but your assumptions about f. So keep in mind, with a p-value, you're rejecting the whole model. So it's not just the hypothesis. So the hypothesis could be correct and your model is not the right model. I mean, I can guarantee you in any real problem, f is not true f. So you gotta be a little bit careful. I think what happens a lot of times is people are rejecting their assumptions. Nice thing about science is if you ever do anything really important and it matters, somebody else is gonna come and look at it. So probably a lot of people that are touching this problem, the problem is just so nuanced that nobody ever really cares. I will say that in some communities, computing a p-value for stuff like that is banned. It's not allowed. So we'll talk about that a little bit. There is a op-ed, an editorial that's on the webpage, so if you want to scan over the course list of handouts, there is a couple statements on p-values. So BAS, the Basic and Applied Social Psychology Journal, banned p-values a few years ago. A lot of ASA came together, they formed two different committees. The committees were like 40 people apiece, and they basically said nonsense, just like you could. So I was really disappointed in our field, where it's like, but it did get set up with a committee to say things. I don't think we should ban things, I think we should try to understand them and understand what the implications are. So I think that's really bad style as well. So just to ban something, sometimes some p-values could be meaningful, so we need to get at the heart of this. But for hundreds of years, it seems like, or at least 100 years, people have not really settled this debate well. This is the most contentious stuff in all of statistics. This is probably why people love saying deep learn and not statistics, all because of hypothesis testing. So they kind of obviate all of that. Who cares? Let's just do some forecasting. David?
Maybe the psychology people, maybe they were, well, you can't use this responsibly, so we're going to take it away from you.
That is what's happened. So in psychology, very, very typically, I don't want to say everybody, but very typically, a psychology PhD. Are there anybody studying psychology in here? Okay. So then I can give my opinion and be totally wrong. But very, very typically, what I've observed is people send off surveys all the time. So what is the distribution of all of that? Basically, you're just rejecting. You're basically just saying people are answering in funny ways and they're a little bit different and you don't know why. But you end up plugging in what your notion of a hypothesis is and you're rejecting probably the IID assumption of everything. Probably rejecting something else. They send off 10 billion surveys, they get back 10,000. So you already have a problem with biases. So why people have returned them, so selection bias, we've all heard about that in our Stat 101 classes. But they have such a large sample size that their p-values are small and they're like, sweet, p less than 0.05, I get to publish and go on my merry way. What is the loss to that? They get published. So their loss function is probably whether they get published or not. If their p-value is 0.06, oh no, back to the drawing board. So, and usually they'll probably argue, well, you didn't have enough power to do the test, so you go to a granting agency and say, give me another $1 million so I can go collect more data. So to drive my power up and my type 2 error rates down, we'll know what all this means probably by this time next week. And my p-value is now small. I could have already told you that was going to happen. So, and they probably are not saying anything about the hypothesis, but they're probably just figuring out that there's weirdness in the data collection compared to their assumptions. And they're probably rejecting that. So, yeah, reproducibility on that stuff is horrid. Okay, we'll talk more about reproducibility later. Let me just introduce you to the likelihood ratio test stack. Just real quick, this is a heads up. This is the device that Neyman and Pearson are using. So all the stuff surrounding the Neyman-Pearson lemma is basically a statement about tests of this form. I need to fill in some more details. Everything I write on the board today won't cover everything Neyman and Pearson are talking about. So this is the likelihood ratio test statistic. You might call this the maximum likelihood ratio test statistic. I hear it called that all the time. It looks like this. Lambda x, that's just my data. So the function of my data is equal to the maximum, where theta is in the null set. So whatever the null set is. So in this test, it's just theta naught, it's just 1 point. In this test right here, it's all the stuff to the left-hand side of theta naught. In this test, the null set is just a point as well. So that's what I mean when I write this thing down, the null set. I take the likelihood function, and I do the same thing in the denominator, but I do it in the alternative set. So I'm going to maximize over the alternative set, the likelihood right there. This is a formulation that can be done. It's equivalent to what the book does. There is a problem in the book that writes it down this way. I generally write it down this way, but it's okay to do this as well, where I maximize over all of theta, where this is going to be an element of both the null union the alternative. So just as a heads up, you do get equivalent tests, but you have to just recalibrate what the thresholds mean. So doing it this way does have some advantages kind of early on. I will point out they moved to the other formulation without really telling you in the book. So just keep in mind those are the same. So they say, oh, there's a problem in the back book that explains that. You didn't read that yet and do that problem? So just keep in mind both tests are about the same, except it just defines the value of lambda a little bit differently. We know this thing is positive because we're taking likelihood functions. So if I ended up taking this over just the whole, if I do this over the whole set, this is guaranteed to be bigger downstairs. So it's going to bound this test statistic between 0 and 1. If I ended up just constricting this to the alternative set, this number could go between 0 and infinity. So we're basically just rescaling the problem. I'll keep it like this, is the way the book first introduces it to you. So when they proved the Neyman-Pearson lemma, they moved to the other formulation. Just keep it in mind. So they are equivalent. So that condition in the Neyman-Pearson lemma is the max likelihood ratio test stat for the simple versus simple. I'll kind of point out also, if I take the simple versus simple test and I kind of budge this stuff maybe to the left over here and this stuff over to the right, I'm going to collect that test. It's going to be exactly that test. So if I end up just thinking about this, what happens to this test in the simple versus simple case, and I start moving theta naught and theta 1, you recollect the one-sided test. So they derive the one-sided test from the simple versus simple test. For this sharp test, everything doesn't lend itself quite as nicely. And the reason why is what we're going to do with this is we're going to threshold on one side of this. So if all of the measures were monotonic using a one-sided threshold, it makes sense. But in the sharp test, there's two sides to this. And that creates some problems with the theory that embraces this test statistic. So in monotone cases where the likelihood function or the likelihood ratio test stat is monotone, you enjoy nice properties. That happens here and here, but not over there. So if you want to dive a little bit deeper into the book from what I'm going to tell you in this class. Sam?
In the simple versus simple scenario, what happens with the maximization over theta equals theta naught? Like, if theta can only either be theta naught or theta 1, then do you actually have to maximize?
Yeah, you just plug in theta naught and theta 1. You only have one candidate value.
Okay, that's what I was.
Yeah, so it still is a maximization. It's the easiest maximization you can possibly take. So what we're going to do is we're going to threshold this, and we have to decide on this value. In this formulation, this number lives between 0 and 1. So that might simplify everything. Let's just look at an example and just clear this up, answer Sam's question, and then we'll be done. So I'm going to jump right to assuming I can use things like the factorization theorem, and I can build my likelihoods either through the product form, or I can just plug my sufficient statistics right in. So what gives me the right to do that? I can factorize this using the factorization theorem, and all those constants would cancel each other. I'm not going to prove that. It's in the book. I think it's probably the simplest thing to conceptualize. I can build my likelihood functions however I want with all of the data points or the minimal sufficient statistic. They're both fair game. So I'll tell you what I mean in a second. So let's say xi is normally distributed with mean mu, variance sigma squared. Let's consider something like this, that mu is equal to mu naught, versus the alternative, mu is not equal to mu naught. So this embraces a little bit of what Sam said in this stuff. So that's just a point. So this is the contentious setup. I don't think that there's anything too contentious about what we're about to derive. It's just what we do next with it that is a little bit weird. So what I'm going to do is I'm going to form my likelihood ratio test statistic. I could do this just like this, maximize over theta is equal to theta naught. So that's the part that Sam doesn't, what do you mean maximize? There's only one choice to plug in there. So yeah, it's a bit superfluous. So a little bit overstated here, but it's the same paradigm. I could do this with a likelihood I goes from 1 to n, e to the minus 1/2 xi minus whatever, oh, I used theta here. Let's do mu is equal to mu naught. So I can do that, divided by sigma squared, and I can do maximum over mu, e to the minus 1/2 xi minus mu. So same likelihood function divided by sigma squared. I could write it down like this if I wanted to. It'll make the arithmetic just ever so slightly more difficult. Add an extra line, or I could just jump to using sufficient statistics. And I can just build my likelihoods out of this. So mu is equal to mu naught, and I could know that the sufficient statistic for testing mu is x bar. That's the minimal sufficient statistic. So if I do inferences off of that probability distribution, I should get the same answers. Proof, the factorization theorem. So keep in mind we're touching likelihoods, everything comes in a ratio, so the only important part that still has the parameter in it is next to the sufficient statistic. So I can write this down. E to the minus 1/2, I could use x bar as my test statistic. So that is minimal sufficient minus mu squared, and it rescales the variance in there. So this will end up being the exact same answer. E to the minus 1/2 x bar minus mu squared over sigma squared over n. And I'm going to maximize over the whole space. So the way they've set the problem up is the denominator is always the maximum likelihood estimator. It's what we need. So we just need the MLE to do this. Sam's already told us this is really easy. So let me just replace that and plug mu naught right in there. That's the only way to maximize. If I were an averager and a Bayesian and I tried to smear mass and average over it, there's only one way to average over one point. And that's why there'll be total agreement in the simple versus simple case. But in the denominator here, the Bayesian is going to treat this very differently than what the Neyman-Pearsonian is going to do. So when I maximize over mu, we all know that the maximum likelihood estimator is x bar. So I just plug x bar right in there. That is the MLE. You guys proved that on midterm 2. So I like it like here just because I get really clean answers real quickly. Just get rid of that, that's 1. You could have done the same thing here and plugged in x bar. Get rid of that. Same thing here, mu naught. You will get the same answers. There'll be a lot of cancellation. I prefer to work with the sufficient statistic. It saves time to write. So this thing is just e to the minus 1/2 x bar minus mu naught over sigma squared over n. That's squared. And what we're going to do is we're going to threshold by some number c. C is going to lie between 0 and 1. So this is called the rejection region. I have to pick C to decide my level of compellingness. Neyman and Pearson, how they pick C is they do it very probabilistically. So they're going to calibrate C to be some probability, so I can make a probability statement about how often this happens. So they usually say, I want to reject, 5% of the time at all costs. It's true, and they'll pick the corresponding C to do that. So I can rephrase everything, and I can just rewrite this criterion like this. So I'll just say, take the log of both sides, so log C, and then I'll multiply by my minus 1/2, or minus 2 on both sides, so I'll just write down minus 2. Over here, that did flip the sign. I should plug in the equal sign. So I'm going to flip the sign over this way, and then I'll get x bar minus mu squared has to be greater than that to end up rejecting. Plug in mu naught right here. I could end up taking the square root over this whole thing. And that's 13. That bothers me just for a second. If I were looking at a test, I'd go, uh-oh. Then I remember, C is between 0 and 1. So that's negative, this thing is positive. And really, all this thing is just some other number. Let's just call it K. So some other threshold, it's related to C. And we can figure out that relation, but basically I'm just going to threshold if, and I should take the absolute value right here because I took the square root. So I need to take the absolute value, just be very careful of that when I took the square root over both sides. And so what it's basically saying is if x bar is very far away from mu naught, we want to reject. And I think that makes sense. So in Stat 101, we were doing stuff like that and computing p-values for this. I just want to tell you what the consequences of all that stuff are. So likelihood ratio test stat kind of makes some sense. We derive some neat statistics. So I do like Neyman and Pearson for a reason that tells us the right test stats to look at. So using the likelihood ratio test does help even if you're not a Neyman-Pearsonian. Let's come back next week and try to talk about these debates, what can go wrong and what can go wrong. Thanks y'all, enjoy the weekend. I'll have the exams for you on Monday. Oh, yes. Sigma squared over n, right in here, so this is sigma root n. So it's the relative distance compared to the standard error. If that thing is large. Yeah, thanks for that. I did want to say that. The example in the book is actually taking sigma to be 1, but I think it's right here.
ratio of like.
I'm good at
So is that
It's the same thing. Yeah, you can do it that way. There's isomorphic forms. So then you get the same thing, yeah. You can flip this around, come up with an equivalent relationship, like flipping it upside down. I did have a conversation with somebody one time